Alright everybody, this is 8.1 graphing transformations. So this unit is about functions. We're going to look at different types of functions, how they behave, being able to identify them, and then we're also going to do piecewise functions. So starting out, we're doing transformations, okay? And then we're also going to do, for this lesson, we're going to do absolute value functions and review exponential functions. Alright, so first off, what I ask people to do in class is to be able to graph these. So just a reminder, x's lie. We can write our vertex. Here will be -4, -1. So right here. And then we'd use our growth pattern. Here, a is 1. And so we'd go over 1, up 1, over 1, up 3, over 1, up 5. And then we'd do it on the opposite side. And then we would just connect their dots. Okay. So if you want to pause and try the other ones. Alright, so vertex for here, it would be 1, 6. So that's about right here. And then a is -2. So the growth pattern, again, for a quadratic is 1 times a, 3 times a, 5 times a, and keeps going, 7, 9, 11. Usually that will be outside of your graph. So here, 1 times a -2 would give us -2. And then 3 times a would be -6. So that would give us a point there. And then we would do it on both sides. And we'll connect the dots. Sorry if this video is not the best. I went over this, finished it, and for some reason the video or the sound wasn't working. So I'm a little annoyed. But, okay. Here is another example. Here we go, we got -4, -5, so that's about right there, I think. And then our growth pattern here would be 1/2, 3/2, 5/2, 7/2, so we'll look something like this. Let's see, I don't want to miss anything. I think that's about right. And then we'll do it on the opposite side. Connect those dots. We'll just keep going. Okay, so there is 3 graphs. Okay, they all have different a values. Some are going up, some are going down. Just a quick reminder on how to do these. Vertex, we already kind of found that. That's our -4, -1. Here we have a minimum. It's the lowest value. Its domain is, the value here would be -1. Domain would be -infinity to infinity. And the range, like how low and how high, that goes from -1 to infinity. Okay, we use a bracket because we include it. So for this example, we said our vertex was 1, 6. Here we have a maximum value of 6. Domain is the same, and range, how low to how high. Oops. Okay. So there's just some things just to refresh. Okay, so each of the equations above are in vertex form. They're the most easiest to graph since you can easily pick out the vertex. Just remember the x's lie. A transformation is a description of how a graph has changed from the parent graph. So the parent graph is basically your equation that has no bells or whistles. So for here, it's just y equals x squared, and it looks like this, where the vertex is at the origin. All right, so how we're going to do is we're going to try and figure out how an equation has been changed or transformed based off of the parent graph. All right, so I just already wrote this down. We can talk about this, but when we did previous units, we said that a, gives us the growth rate and it opens up or down. With transformations, we're going to do the same sort of thing, but the way we write it is a little different. So if a is negative, it says that it is, we will write down that it is reflected over the x-axis. So that's where it takes something like this and then it flips it so it looks more like this. Okay, so that is reflecting. All right. Then we're going to look at the number, not the sign, just the number. So if the absolute value of a, so let's say that a is -2. then we're only going to look at the 2, because the absolute value of a negative 2 will just give us 2, okay? So if the absolute value of a is greater than 1, what does it do to the graph? Well, it vertically stretches it. So if we looked at this graph, if we compare A and B, A has like a value of 1, and B has like the absolute value of A would be 2. As you compare those two, B looks a lot like it's like skinnier or taller, okay? And this is the word that we would use, it's vertically stretched. All right, so for B, we would say it's vertically stretched by a factor of 2. And again, we don't use the sign, we just say the number. So we wouldn't say vertically stretched by a negative 2, we just say it's vertically stretched by 2. The negative, we use that for the reflection over the x-axis. All right, and then if a is less than 1, the absolute value of a is less than 1, then we say it's vertically compressed. So for C, we look at that, and it looks like it's more fat. It's been like squished. So for B, it's like we have a taffy that's being pulled. It gets skinnier. And then for C, it's like we're stepping on that taffy, and it's becoming much wider, okay? So that's what those two things that A does. So if it's negative, if A is negative, it's being reflected over the x-axis. And if A is greater than 1, it looks like it's being stretched. It's more skinny, vertically stretched by a factor of 2, or vertically stretched by a factor of 4. Okay, and if A is less than 1, like a half or a third or 3/4, okay, then it's vertically compressed by a factor of a half or 2/3 or 3/4, okay? And then we're going to talk about H and K. So H and K, if we look at our graph, basically it tells us where the vertex is. That's what we used that for in the past. But when we say H and K, H basically puts that vertex left or right, okay? And the K makes it go up and down, all right? So if we look at this graph at the top, let's just compare this, all right? If we had the graph at the origin, well, what's happened with the H? Well, the H moves it left 4, and the K makes it go down 1. Maybe I should use a different color, okay? So it made us go left 4 and down 1. So that's basically what we'll say with our transformations, all right? So for this example, this is making it go right 1, because x's lie. All right, and then K makes it go up 6. All right, here's another example where it's going left 4 and down 5. And the word we use for that is translated. Okay, maybe in the past you use shapes, and you can translate it, or and make it go up or down or somewhere around in the graph. Okay. So keep that in mind. You might want to pause this and write all this on your notes. This is very important when you get to some of these problems. All right, next we have is absolute value functions. What do absolute values do? Well, they make anything, and just like we did up here when we said the absolute value of A, it makes anything positive. So like the absolute value of negative 2 is just 2. The absolute value of 2 is also 2. Okay. One thing you should be aware of, if you have an equation like this, I don't know, x minus 2, okay? This doesn't magically make that become a positive 2, okay? It stays as a negative until you evaluate what's inside that absolute value, and then you evaluate that absolute value, okay? So just, if that makes any sense, it's okay to have negatives inside. It's not going to make it be positive until you plug in like a 1 here. Then you'd get 1 minus 2, and then you'd get 1 minus 2 is negative 1, and then that would end up giving us a positive 1. Okay? So anyways, absolute values make anything, when you evaluate it, it becomes positive. All right, what do they look like? What does an absolute value function look like? So we'd want to maybe start with the parent graph of a linear equation. Okay, this is like y equals mx plus b, where m is 1 and b is 0. So the y-intercept would be 0, and we'd go up 1 over 1, up 1 over 1, up 1 over 1. Okay, and the other direction. But when we have an absolute value function, let's just see what happens. If we plug in 0 here, well, we would get the absolute of 0, which is just 0. And if we plugged 1 in there, we'd get 1. If we plugged 2 in, we'd get 2. And 3 would get 3. So it doesn't do anything if you plug in a positive number. It doesn't change it. But if we were to plug in a negative 1, then that would pop out and give us a positive 1. So basically, it takes all of these negative values here and makes them become positive. Okay? So it would end up looking something like this. This is what the parent graph would look like. It's vertex, just like the quadratic. The vertex is at the origin. Okay? But you notice that it's more like a V shape. It's not a U like a quadratic. They have straight lines, no curves. Okay? All right. So here is the transformations for an absolute value function. This is the equation for an absolute value function. You probably noticed that it looks very similar. It's written the exact same way as a quadratic in vertex form. The only thing you should be aware of is that we have absolute values and there's no square. Okay, there's no exponents for an absolute value function. Okay, so everything else here is the same. You could rewrite what we wrote above, or you can just write something like C, the quadratic transformations above. Okay, so I just copied those. And you can't do that on your notes. So let's graph some of these absolute value functions. Okay, so again, it's very much like vertex form. This is your vertex. X's still lie. So our vertex here would be -4, -2. And then the thing that's different than a quadratic is A, like for this example is 1. That's our slope. That's our rise over run. So like 1 over 1. So we would start at that vertex and we'd go up 1 over 1, up 1 over 1, and we would keep going until we're out of our graph. But the thing that's a little different too is, or I guess maybe it's kind of the same as the quadratic, is it's symmetric over the axis of symmetry. So instead of continuing going that direction, we would want to mirror it over the axis of symmetry. So that's what gives us that V shape that we're looking for an absolute value function. All right. So here's another example if you want to pause and give this a try. So our vertex here is 1, -4. So that's like right here. And then our rise over run is 1 over 2. So we'd go up 1 over 2, up 1 over 2, up 1 over 2, and then mirror it to the opposite side. Connect the dots. Probably put some arrows on the edges. Okay. As you notice, it's more wide than the other. It makes sense because this one also, just like for quadratics, we would say because A is less than 1, it is vertically compressed. Okay. All right. Last but not least, if we want to plot this one, looks like we'd have a vertex here and we'd go over 1. This is like -3 over 1, so rise over run, we go down 3 over 1, down 3 over 1. Okay. And just like quadratics, if A is negative, it's opening down. So you can always keep that in mind when you draw your graphs. If it's opening up and A is negative, then you made a mistake. All right, so transformations, we'll get into that a little bit more right here. Okay, so these are the types of problems. Some of the problems that you'll have on your homework is I will tell you what the parent graph looks like, and then another equation. And we want to write down all the transformations necessary to turn f of x into g of x. Okay, so how we do this is we'll start left to right. First thing we run into here is this 4. That's a little different than what's above. So we need to write something about that. Okay, again, that is that tells us that it's vertically compressed, or sorry, vertically stretched, because it's more than one. So vertically stretched, I'm just going to abbreviate that to VS, vertically stretched by a factor of 4. Next thing we run into, this is all the same, and then this is new. So what does that do to the graph? Well, that translates it up 5. Translate up 5. Okay, and that's all we need to do for these types of problems. So here's kind of something that's a little different. Let's see what we have here. So again, we start left to right. First thing we see here is reflected over the x-axis. Next thing we see that's not for f of x is that it is vertically compressed by a factor of 1/3. And then this is also not above. So this is telling us that it is translated right. Again, x is lie, so right 7. Okay. If you had something that you also had some like up 3, then you can just say and up 3, so that you don't have to like write another bullet. But either way would be great. All right, and then next for number 2, these are basically the same, just going backwards. So I tell you what the parent graph is and the transformations, and you just need to write the new equation after the transformations. So here we have g of x, so this is like our second graph, and then this is saying that it's being reflected about the x-axis, so that tells us that we have this negative. Vertically compressed by a factor of 1/4, so a is negative 1/4. And then it says it's translated up 1 and right 2. So again, this is a quadratic, so we'll do some sort of like parentheses squared, and we'll do x minus h. So again, h is like our left and right. It's going right 2. So again, x is lie, so we'll do minus 2. And then it's going to go up 1. All right, so why don't you pause and give this one a try. All right, it is also a quadratic, so we need to have some sort of like x squared or an exponent somewhere when you're done. Okay, it says vertically stretched by a factor of 4, so that's just our a value, and it's not reflected. We know it's not negative 4 because it doesn't say that it's being reflected. Then we're going to say we have our x something squared. It's going left 3, so that's like minus 3, but x is lie, so plus 3. And then it's not going up or down, so we're all done there. All right, this is an absolute value function. This, again, we'll do g of x, and it says it's reflected, so we know that a is negative. It's vertically compressed by 1/3, so a is negative 1/3. And then we need to do absolute values. Don't do parentheses squared. It says it's translated down. So it's not going left or right. So we'll just have this x, and then we'll close our absolute value, and then we're just going to go down 2. All right, when you pause D. Okay. So here we have vertically stretched by a factor of 4. I need to change that because it's the same as B. And then it's also an absolute value, translated right 2. So again, x is lie, so it's going to go negative 2. And then it's down 3. All right. You may also want to be able to like write equations from graphs. We have done this before. So how we do that is we find that vertex. Here it's 1, 3. And we can find our a value. Again, it's always over 1, and then we'll just go whatever way it takes to get us to the graph. So down 2, so negative 2. And then we can just write down our equation. So this is a quadratic. How do we know? Well, it looks like a U. Okay, it's not straight. It's curvy. So we got y equals negative 2 x minus h, so net x minus 1 squared plus 3. So it's not much different when we have our absolute value function. Looks like I didn't erase that all the way. Okay, so what we're going to do is we'll take that vertex is, 0, -3. That's like your h and k. And then same sort of thing. To find what a is, we can go over 1, and then it's just 3. It goes up 3, so a has got to be 3. If you prefer, you can also just go rise over run. So you can go up 3 over 1. So either way, you'll get the same thing. So we'll write our equations. So y equals a, absolute value of x minus 0, but that's just x, and then we'll do plus k, which is a -3. So here's another example. Looks like I didn't erase that all the way off either. So here you start with your vertex. Looks like it's -1, -3. And then you can do rise over run, 1 over 2. So a would be 1/2. Or you could go over 1 up how much, and that's 1/2. So either way, you get the same thing. So y equals 1/2, absolute value of x minus h, so plus 1, and then -3. Okay, so last thing we need to talk about. Sorry, I know this is a little long, but I really feel like it's not too much to take in. Homework wasn't too bad for most of the students. All right, so a review on exponential functions. So here's an example of an exponential function. A is your initial value. There's always 1. Okay. Whether you can see it or not, if you can't see it, it'll be 1. B is like the base for your exponent. It's the growth or decay factor. And then x is just your exponent. Typically in exponential equations, x is your time. So we use that a lot when we do like interests or mortgage rates or things like that. You can calculate how much you're going to earn or how much you have to pay or things like that. All right, so here, just a quick review on how this looks. So if we were to plug 0 in here, 2 to the 0, again, is just 1. If you want to talk about that, come and talk to me. If you plug 1 here, that's just 2 to the 1, which is just 2. If you did 2 squared, that's 4. If you did 2 to the third, it'd be 8. So you see it's just doubling. So you can kind of do that same pattern to go the other way. And this is what an exponential function looks like. It's always growth whenever the base is more than 1, because that's what's being multiplied every time. If you do 1.1 times 1.1, it's going to be bigger than what it started with. Okay. All right, here is an example of exponential decay. Again, if we plug 0 in here, would get 1. If we plug 1 in, would get 1/2. If we did it squared, 1/2 times 1/2 is 1/4. And it just keeps getting halved every time, smaller and smaller. And you can go the opposite direction, and this is exponential decay. One thing we should realize is that this never touches 0, just gets halved every time, gets smaller, 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 but never gets to 0. All right, decay is whenever the base is less than 1. So like 1/2 times 1/2. Half of 1/2 is getting smaller, and then half of that again gets even smaller, and half of that again gets smaller. Okay. Now let's talk about rates. So rates is a percentage change between each output. So basically let me write this down and see if you can figure out what the rate is. Or I'm going to tell you what the rate is. You're going to write down how we come up with that. So the rate here is 23%. The rate here is 64%. The rate for H is 30%. And then here the rate is 60%. So what do you notice? Okay, I think for the left side, I think that's the easiest one, because you kind of see that decimal that's the same. It's just written as a percentage. So for all of these, the rate is just the difference from 1. It's how much you gain every year or month, or it's the percentage you lose every day or month, okay? So if you wanted like a formula, you could just do, this is what you would write down. You do something like, it's always going to be b minus 1, and then we'll times it by 100. So we're doing the difference from 1. So how far is this from 1? Well, it's 0.23. And then we are moving the decimal twice. That's the same as just multiplying it by 100. And that would give us 23. Okay, so difference from 1 here would be 0.64. We move the decimal, and we get 64. All right, so when it's growth or decay, when it's decay, again, we want to know the difference from 1. So how far is this to 1? Well, it's 0.3, and then we move the decimal twice, and we get 30. So same sort of thing. How far is this from 1? Well, it's 0.6. Move the decimal twice, and we get 60. Okay, so if you want like a formula for that, basically, same sort of thing is we want to do the distance from 1 times 100. Okay, so those are just, the 1 and the b are swapped so that we end up having a positive value. We'll never have negative rates. Okay. All right, so these are the types of problems that maybe you ran into in the past. We need to just identify the stuff. So the initial value, bam, 4. Growth or decay, it's decay because it's less than 1. Its factor, 0.78, and its rate, again, is the difference from 1. So what would you have to add to that to give you 1? Well, it would have to be 0.22 or 22%. And then here's an example of growth. Its initial value is -3. Its factor would be 1.47, and then 47%. Okay, so maybe that's what you saw in the past, but these ones are a little different. What do you notice between 6 and 7? All right, so maybe you notice that there is a number in the exponent. Okay, but the thing is that the equation that we have for calculating or finding the factor and the rate is only when it's a times b to the x. So we need to make it look like that, and it's not too bad to do. All you need to do is evaluate this. In a previous unit, we talked about like exponents on top of exponents. 1.25 squared to another exponent, let's say x. And if that was the case, we could just multiply those together. And that's what's going here on the left. But we can easily go the opposite way and just evaluate the 1.25 squared. So if you do that, you end up getting, you'd want your calculator, oh boogers, I don't think I brought that. Give me 1 second. Calculator. Okay, so what you'd want to do, typically on your calculator, you'll find a button for like a TI. It's right above the division button. It's like an upside down V. It's called a caret. That makes an exponent. Okay, you can find something similar to that on most calculators or on your like your phone. Okay, so you'll type in 1.25, and then you'll need to find your exponent button. Sometimes you can just do the squared button, and here I get 1.56. We'll round to 2 decimals. So this is exactly the same as that. Okay, but now we can write down our initial value. Here the initial value, you can't see it. It's got to be this like 1 in the front. Okay, and this is growth. Its factor is 1.56, and its rate is 56%. Okay, so here's another example. Again, you'll need to just evaluate this. So get your calculator, 0.68, and then to the third. I end up getting 0.31 to the t. So initial value, again, for this one you don't see it. It's up here in the front a bit. I can't see, invisible. So it would be 1. And then it is decay factor of 0.31. And then the rate, again, is the difference from 1. So that would be like 0.69 or 69%. All right, last but not least, initial value is 2. So you notice that the initial value doesn't matter. We're only evaluating the base and its exponent. So we'd end up getting 2 times whatever that will be, 1.1 to the third. So I end up getting 1.33 to the x. So we have growth. Its factor is 1.33, and its rate is 33%. All right, so I hope this helped you. If you have any questions, please come and talk to me, and we'll see you later.